Okay. Hello, my name is Melikhan Tanyeri. I'm a postdoctoral researcher at the Department of Chemical and Biomolecular Engineering at University of Illinois. Today I'm going to talk about the NanoHub tool that we have developed for hydrodynamic particle trapping. So I'll briefly describe this method and then show you how the tool runs. So this method is a microfluidic flow-based method for trapping micro and nanoscale particles, and it's based on planar extensional flow, which is generated by two opposing laminar flows, which meets at a microchannel junction. And in this tool, we briefly show have an image of the microchannel junction. Basically, we have two opposing laminar flows meeting at two intersecting microchannels, and these flows basically exit the microchannel junction along the perpendicular direction and in opposite directions. And by doing so, we create a stagnation point at the microchannel junction, through which at which we confine and manipulate particles. So this is the working principle. We create a stagnation point and we confine particles at this stagnation point. And this NanoHub tool basically gives us a snapshot of what happens when a particle enters the microchannel junction. So at the tool, you'll see different parameters that are affecting the trap performance. First of all, you can determine the total simulation time, so for how long you want to run the simulation. Another important parameter is the particle size. So you can determine particle size. You can have a nanometer size or a micron size particle, and then you can basically test how the trap responds to different particle sizes. Another important parameter is the initial position of the particle. So you can place the particle at any position at the microchannel junction and then see how the particle behaves with the trap. Another important parameter is the flow parameter called strain rate. Strain rate basically gives you a feel for how fast the flow runs through the microchannel junction. So basically, its flow rates, which is divided by a characteristic dimension of the microchannel, for example, width or height. And so you can change this and see how the strain rate affects the particle trapping performance. We also, since the particle is a Brownian particle, it can diffuse, we added temperature as a parameter. So as the temperature increases, the Brownian motion of the particle increases, and you will see how this affects the particle trapping. In the future versions, we may just add viscosity as another parameter. And finally, this type of flow creates a semi-stable flow potential at the microchannel junction. And therefore, we need to apply flow control along the unstable direction, which is the flow out direction. And we added two parameters. One of them is the proportional gain parameter, and the other one is the feedback delay time parameter, which you can change and see how it affects the performance of the trap. Just to briefly go over the parameters and how they affect the trapping performance, let me give you a quick overview. As you can guess, as the particle diameter increases and the temperature decreases or the viscosity increases, the particle shows less Brownian motion. Therefore, the precision of confinement, or the ability to trap the particle and confine it to a specific spot, is increased. So larger particles can be confined easier. If we use a viscous medium, it helps with trapping particles, and if we decrease temperature, it helps with particle trapping. Strain rate is another important factor, and it's not that trivial. Along the flow-in direction, as you increase the strain rate, the particle can be trapped to a smaller region, whereas in the flow-out region, typically the excursion of particle increases as you increase the strain rate. And with control parameters, there's a certain range where the proportional gain helps you to confine particles better, and there's a certain range beyond which the particle is unstable and it escapes the trap. And certainly if you can decrease your feedback delay time, it helps with particle trapping. So you'd be able to vary these parameters and within the given ranges, and then run the simulation. And what the simulation does is it basically runs a Brownian dynamic simulation of the trapping as the particle enters the microchannel junction, and then it will record particle position and stagnation point position dynamically and capture frames of each simulation run, and then at the end of the run you'd be able to see it as a movie.